we're going to learn the squeeze theorem. This is still on that second 1.4 set of notes. The squeeze theorem does what it says. It squeezes a couple of functions together. So it's a little bit weird, but let's go ahead and draw it. I would recommend watching the first time and then drawing it for yourself the second time. So here we go. We have three functions, h of x, f of x, and g of x. And we know that h is always less than or equal to f, and f is always less than or equal to g. Okay, so this one is always the lowest function, this is always in the middle, and this is always up above. However, with the equal signs, any of these functions can be equal at any spot, but if they're not equal, then this one's below, middle, and above. Okay. So let's draw a function for h of x. I'm going to draw h of x like this. The next thing I'm going to draw is g of x. So let's draw it like this. Okay. I've drawn these two functions in a very particular way because right here, they actually meet up at the same spot. So let's name that x value c. So we are told that at some point, x equals c, the limit as x approaches h of x, the limit of h of x as x approaches c equals L. All right, so here's c, which means that this y value is going to be L. Put that here. Right? The left side and the right side have to meet up. We also know from this that the limit of g of x as x approaches c equals L also. So that's why g of x comes down and has that point over here as well. Okay. Well, if we know that this is true, and we also know that f of x has to be between these two functions always, because that's what this means. Let's draw that in here. Okay, so f of x can do whatever the heck it wants over here. It can go up high, it can go down low, but it has to be stuck between our two functions, h of x and g of x. But when we get close and close and close to c, notice that f has to be squeezed in there. It has to be between. And then it can do kind of whatever out here, okay, as long as it stays between h and g. Okay, so what's happening as f of x gets really, really, really close to c, f of x has to be between or equal to h and g. So we know that this spot has to be the point CL as well. So that means that the limit of f of x as x approaches c has to exist, right? We can't have the jump discontinuities where there's like one above and one below, and we can't have goes to infinity because these guys don't go to infinity. So that limit of f of x as x approaches c has to exist, and it also has to equal L. The limit can't be below or above because it's stuck in between. So that's the squeeze theorem. All right, next one, making piecewise functions continuous. So that's all we're doing with the squeeze theorem, making piecewise functions continuous. Let's say that we have a function that looks like this. F of x is this piecewise guy. For a piecewise function to be continuous, each function must be continuous on its specified interval. Let's stop there. Sine of 2x has to be continuous where x is less than or equal to pi. Well, sine is a continuous function, right? It does this, just up and down. 2x plus k. So k is some kind of a constant. We just don't know what it is. This one's also continuous. Okay, k is definitely not like a variable. It's a specific number for this problem. We just don't know what it is yet. Okay, so 2x plus 1 is a straight line. We don't know what its y-intercept is, though. Straight lines or any polynomial functions are going to be continuous everywhere. So really what we just have to do is make sure that our two sides meet up. Okay, we want to make sure that we don't have a jump discontinuity, because piecewise functions, if sine does this and then our line does this, we are discontinuous where they meet up. They don't actually like meet. So we need to make sure that this is what it looks like instead. Okay, so if we're continuous here and continuous here, we really just have to make sure that the limit from the left-hand side as x approaches c and the limit from the right-hand side as x approaches c are the same thing. Okay, so let's do that. I'm going to use pink for the top one, and how about green for the bottom one? Okay, so we know that each of those is continuous, except we don't know that they meet up. So we need to say that the limit as x approaches pi from the left side, right, the less than of sine of 2x, is going to equal the limit from the right side. So limit as x approaches pi from the right side, which is the plus, of 2x plus k. Notice that I'm putting the 2x plus k in parentheses, so it doesn't look like we're taking the limit of 2x and then just adding k on. All right. Well, we can take the limit by plugging in pi and seeing what happens. Let's do it. So sine of 2 pi, sine of 2 pi is 0. So the left-hand side is totally evaluated. We have found the limit from the left side to be 0. So that means that the right side limit is also going to equal 0, right? Limit as x approaches pi of 2x plus k. All right, so when we plug in pi in here for x, we get 2 pi plus k, because k is not x. Well, there's nothing really we can do about that. Let's bring it down. 2 pi plus k. So the left-hand limit has to equal the right-hand limit. Let's solve for k, because the problem says, for what value of k? So let's subtract 2 pi from both sides, and we end up with negative 2 pi equals k. That means that right here, this is supposed to be negative 2 pi. For any other value of k, we would get a jump discontinuity. For this value of k, the two sides match up. Okay, let's do another one. For what value of k is this function continuous at x equals negative 3? Well, our first function, x squared minus 9 on the bottom, if you plug in a 3 or a negative 3 down there, this fraction would not give you an actual value. The function is undefined at x equals 3 and negative 3, except our function in general, f of x, is going to equal k at x equals negative 3. So really, we just want that value of k to like plug the whole of this to make it actually continuous. So here's what we're gonna do. Do the top one as pink again, bottom one as green. So the limit as x approaches negative 3 from the left and from the right-hand side, they have to actually equal the same thing. So that's both. Don't have any whiteout, so we'll just leave it alone. Okay, so the limit of 2x squared plus 5x minus 3 over x squared minus 9 is going to equal the limit as x approaches negative 3 of literally just k. Those are going to be your limits. All right. So over here, there's no x's. This one's a little tricky, but there are no x's, so there's nowhere to plug in negative 3. That means this side is literally just k. Okay, left-hand side, the limit as x approaches negative 3. Now we talked about how when you plug in negative 3 down here, you get 0. Does that happen on the top as well? Negative 3 squared is 9. 9 times 2 is 18. Over here, 5 times negative 3 is negative 15. So 18 minus 15 minus 3 is also 0. So we talked about how we can rewrite limit and then factor on top and bottom. Since there is a whole, right, we got 0 over 0, we know that one of the factors has to become 0 by plugging in negative 3. So we use the opposite one, the opposite number here from that, right? If you plug in negative 3 here, you get 0, negative 3, you get 0 here also. All right, denominator, that's going to be an x minus 3 as the second factor, and on top, x times 2x will give us that 2x squared, and here 3 times negative 1 gives you that negative 3. Do the double check. 3 times 2x is 6x. X times negative 1 is negative x. So 6x minus 1x is that 5x. So we factored correctly. All right, we are going to now cancel out that whole factor. And then we can go ahead and plug in negative 3 here and here. So on top, 2 times negative 3, negative 6 minus 1 is negative 7. On the bottom, negative 3 minus 3 is negative 6. Okay, there's nothing to do on the right side, so just bring it down. And we can simplify this slightly, so not negative, positive 7 over 6 is going to equal k.